for federal Minnesota. Independent state, Wisconsin. You'll send out a copy of your 1040. Just send that copy.
And then I send this, and that's in New Mexico.
You'll send New Mexico. New Mexico.
No, and that's New Mexico.
Okay, I think we can do our quick meeting. So who we are and what are we going to do? Huh?
Nothing.
No? No suggestions? No. So where did we stop last time? And what did we accumulate by now? Huh?
High pulse?
Yes. That's correct. What else?
Photon echo?
Yes. But between pi pulse and photon echo, where did we go? Huh? In terms of physical effects of the observations, Brandon is the biggest expert in the room on this effect. And he was introducing the three-letter abbreviation during his presentation.
FID.
Yes. Can you repeat and explain to the rest of us?
FID, so free induction decay. So, say what it is.
Yes.
So it's like when we excite the system and then monitor over time in order to determine its relative populations over time.
Not populations. Okay, let me repeat. So we'll better spend less time in vanishing time on MATLAB and more on talking, because concepts are more important. So how do we characterize the two-level system, no matter for optics or NMR experiment, if you want to know everything about quantum state and have a possibility to be away from pure state? Which observables? No. Sphere of magnetization, and some of you were spelling it like block, like building block. No, it is not block. It is block. CH. So one magnetization. Based on the quantum state of this two-level system, one can find three projections of spin that are related to magnetization, right? And if system is in ground state, it is on the North Pole. Good. And then if we irradiate it by like pi over 2 pulse, it will be on the equator. Equatorial. And what happens after we wait long enough? If there is only pi over 2 pulse.
If that's all you do?
Yes.
It stays there.
But if it is an ensemble of multiple similar systems. Huh?
The block factor will vanish.
Yes. And this effect will affect only projections on X and Y. So if we average our distribution of different transition energies, then we are getting each of these block vectors for individual representative of ensemble will rotate with a little bit different rates, and after averaging we will get 0. So this disappearance of the total magnetization is free induction decay or dephasing, right? But you know from your background education that there is also a depopulation. What you were trying to say, but it is a completely different thing. Well, not completely, but different mechanism. So if you excite something if you promote something from ground to excited, it will not live there forever. It will return back to the ground. So we are going, and this is depopulation. This is relaxation. This is dissipation of energy. And we are going to start this area. If you are doing surface hopping, it is same thing just from different angle. How the occupation of excited states disappears and reappears in ground state. Okay? So those are two different mechanisms, two different phenomena. One is dephasing, which affects only X and Y projection, and another relaxation that affects SZ projection. They need different approaches to model them. And before we took into account dephasing for this X and Y, starting from today, we will make an effort to see how the SZ projection is changing. Before, our SZ projection was changing as a result of applying pulse, right? Or if we just select initial state, just voluntarily, free volus. But what happens afterwards? With all luggage of skills, by now we do not know how to model dissipation of energy, relaxation from excited to ground. Well, we have few hints from Aaron, who started covering this aspect in his presentation, but we still need to bring meat to these bones. So, who we are and what are we doing? What is our goal? How will we formulate our meeting? Just, well, it's very informal, just give some vision. So we probably will stay within two-level system, one box sphere, otherwise it will be too complicated. But our major goal is to provide modeling, provide some mechanistic approach that will show how the excited turns into the ground, or at least starts going there. Okay? Will you be able to make this reminder tomorrow? So it will be our general goal for the next chapter, for next several meetings. So how to relax is our purpose. Not for us, but for the quantum system. What do we know? What can we model by now? What does change population in the scripts that are available to us? I'm going in cycles and returning to the same idea. There is nothing new. How do we change population? Perturbing by outside electromagnetic field, right? By pulse or continuously. Okay, now we know that there is a resonance irradiation. There will be cycles of excitations, de-excitations. There is no irreversibility. It will go with conservation of total energy. If the, as Javid was showing, if there is a mode of electromagnetic field, the energy will go there and back to this two-level system, there and back. But we want irreversibility. We want energy to depart from the system forever, or maybe arrive to system and forever, but come to thermal equilibrium. How do we do it? What are our concepts? Can we make connection to what we already know? So before today, we did have what? we did have one mode, or if it is a semi-classical, it was a monochromatic light of a given frequency. And we provided the shapes for the amplitude, right? For the pulses. How can we prove that in the nature there is only one mode? Can you prove that there is only one mode of the electromagnetic field in the universe? So it was a very big approximation. So we need to take the model that Javid presented and enrich it by multiple other modes. So suppose that we have the same model as Javid introduced, but instead of coupling two level systems with one mode, we will have several of those. Even if their frequency is the same, we just need to take into account that there are a lot of them. Or if you look on the presentation by Aaron, do you remember when he presented a figure with balls and springs? The stuff with many balls connected by many springs. So you just touch one and then energy distributes to all degrees of freedom. Even if all springs are the same, it is many degrees of freedom and it can accommodate a lot of energy. So this is a background philosophical ideas. So it was some time for turn around more, magnify, enlarge. No, wrong direction. I'll cheat. Do not whistle. Good. So before we did, okay, this is a threshold. Before we did ensemble, right? We considered that we have one two-level system with omega 1, another two-level system with frequency of omega 2, another two-level system with omega 3, and they all are irradiated by the same light, right? And then we made an average. We added together their properties in the framework of density metrics and got the, what did we get? Statistically averaged density metrics, averaged over ensemble density metrics, or averaged over ensemble Bloch vector. Statistically averaged density metrics or Bloch vector. So this approach that you have successfully run and tweaked and were able to manipulate and explore the photon echo covers only dephasing, only the process when the length of this Bloch vector decreases, getting shorter and shorter. Okay? But now we want to cover the process when we excite it to the equatorial or maybe to the south pole, and then we want it to return to the north pole. Well, I will tell you that it is much easier to model how it returns to the center rather than to the north pole, but the general approach that we will do is you'll give us a way to this process. So at temperature equals infinity, if you return always to the center, at temperature equals to 0, if you return to the north pole, and at the ambient temperature, it will return in the midpoint between them. phenomenologically. This can be described by adding relaxation constants, this longitudinal and transversal times to the Bloch equation. T1, T2 for longitudinal along this field that will give the relaxation as the phenomenological constant, and transversal for the x and y. So we already have the procedure of averaging over ensemble, but we do not have procedure to take into account multiple modes of environment. So we need to consider our two-level system that has given frequency. We are not going to change it. Well, we are going, but it is not so important. We can or we can omit. But now it will interact. It will interact with several modes. So yesterday, Jagat told us that a mode of electromagnetic field is a harmonic oscillator. It was a background for him to use the representation of this creation and annihilation operators. One two-level system, one oscillator. Now let's consider that we have a lot of them. And I will redraw this figure in a little bit different shape. System 1 with oscillator 1. System 0. System with frequency 0 interacting with oscillator with a little bit different frequency, omega 2. System, the same system, it's replica, omega 0 interacting with oscillator omega 3. So if we find a way to implement this idea, this methodology, then we will be able to describe how the excited state returns to the ground. But what is shown here is already, you see these levels and offset between them. So here it takes into account the quantum features of the environment. This is correct, but it is a little boring and too long. What if we consider that each of these oscillators is a classical oscillator? So it just oscillates. So let's see that our two-level system, which can be either spin or excited molecule, is coupled to some vibration, which also can be either electromagnetic field or like nuclear mode, but something harmonic in resonance. Okay. And this oscillation is not quantized. It is just position and momentum oscillating harmonically. On one hand. On another hand, we do want thermal equilibrium. How do we address thermal equilibrium in the classical mechanics, or starting from classical mechanics? What happens if we hit something? If we have an ensemble of similar systems and they are heated up, will be there any similarity or difference between this? Yes, Boltzmann distribution. What in energy? Okay. Yes. So we can give them different amount of energy. But what about the phase of their oscillations? Will they all have the same phase and move coherently, or each of them will move wherever it wants. Yes. So it will be random motion of all representatives of an ensemble. So what we can do very quickly, and capturing the major effect, is to forget about these quantum levels, but assume that they move starting from different positions. This one starts here, this one starts there, this one starts in the middle. So they have same frequency, but they are going randomly. And sometimes they collide and randomly change their phase. So it was to the far left, suddenly it starts to the far right. So same energy, no Boltzmann distribution. We will take them having, but different phase of oscillations randomly. And then we will treat the perturbation of our two-level system by such oscillator that has certain energy but no information about phase, can start a little disorderly. There is a disorder in time. Can start here, can start there, and randomly change its phase. And repeat the same modeling again and again. So we want to consider interaction of our two-level system with many oscillators, each of which has certain energy but oscillates randomly in a sense of amplitude and initial phase. There is a, let me prove this modeling and invite you to contribute it, that if we do adding together this quantum to classical interacting system and add it up together, then again we will get statistically averaged density metrics that will reproduce as the return of the Bloch vector to the center of the sphere, no matter where we excite it. Any objections or questions? Right now we are doing maybe most important part of the whole course, more important than on the lectures. So please object or argue or ask questions. So it means that no objections. It seems reasonable. Or it seems too strange to believe it. So you just don't want to object it because you do not believe it completely.
No, I do believe it.
Oh, okay, good. Thank you. So what is our practical step? We are going to assume that there is we will take the code that has strong field that induces Rabi oscillations. But then we will assume that this Rabi, in addition to the strong field, there is a very little background field. This amplitude may be 100, 1,000% less. But then the amplitude of these oscillations, which will happen with the same frequency, will be randomly changed each like 10 steps or each 100 steps of the dynamics. And length, how often the phase will be changed, is a so-called correlation parameter that Aaron has introduced. So if it is short correlation, then it will be changed often. If it is longly correlated, then it will be changed rarely. And upon we do it for one system, we see what happens, and then we repeat average over an ensemble. This is the plan. So there are two scripts. Can you tell what are their names?
By ensemble equal center.
And second?
Pulse time.
Okay, I think the pulse pi is the one with a shorter name. Doesn't have average over ensemble. It will be just one system with background field of randomly changing.
The first page of the handout.
Mm-hmm. Okay, so let's open the MATLAB and see how does it work. So you do see that we have we have several lines that model the exciting pulse. How do I do it? No. Yes. I have an idea. There should be an option to share the screen, and then it will cover it. Better?
Yeah.
Okay, very, very good. So here is something that we were touching last time. We developed the envelope function for the pulse, right? And now we can turn it because it doesn't go anywhere anyway. So, and upon we set up the profile, which is Gaussian profile here of the certain amplitude, we are using this variable f to determine the Rabi frequency, like transition dipole times intensity of the field, that will determine the pace of oscillations. And we know that for this pulse, we intentionally promote it from ground to excited, if you select certain intensity. Let's contribute maybe 5 lines more. Well, they already contributed, but we can look on them. So here we are using F0, which will be contribution to the Rabi frequency because of the background radiation of the vacuum, or something that does exist around the system, even if we do not apply intentionally pulse or any radiation. So it will be ground state fluctuations. Because of the quantum nature of any oscillator, there will be non-zero amplitude even if it is in a ground state. And if there is some temperature, it will be of a little higher amplitude. And then the value of this amplitude will be assigned to a random number, random value, if at each time step we are falling within a certain range. So here we are throwing a dice. So R, A, and D is a random number between 0 and 1, and percent is a parameter that we can say, let's say, be 0.1, which means if you compare random number with 0.1, then approximately once per 10 experiments, we will have yes, we will have agreement. So in average, once per 10 experiments, the phase will be changed. And if this condition is not fulfilled, the phase will not be changed. And the parameters of this A, and P0 and percent are set up at the very beginning. So let's run it. And see what happens. So you do remember how this picture looked like when we didn't have any influence of the environment or any influence of the distribution over an ensemble. We did have the so let me remind what we have. So blue line is occupation of which state? Ground state. Red one is occupation of excited. And at the time between about 150, there is a pi pulse, label here is not correct, it's pi, that converts completely from ground to excited. And then you see there are these random changes in population. Because of this little field, if you see on this black line near the x-axis, it has largest amplitude when the pulse is applied, but even away from this time, there are some random values of the electric field, which model the ground state background fluctuations, non-zero field with random phase. And if we contribute influence of this field to the evolution of the system, it will have the change in its population. Make sense? But it is very non-physical because it shows influence of only one mode. In fact, the number of such resonant modes is always large, and there should be collective influence of several of those. Let me bring. Well, if you are curious, if you are interested, you may plot the variable f0. Just type a command, plot f0, and you will see these fluctuations of in the background. Double F. Double F. Double F0. See, it shows something senseless. You wouldn't argue that it is random. It's hard to. If you do Fourier transform, it will never be equivalent to oscillation, right? And it is amplitude. If you do FF without zero, it will be this random thing plus the pulse at the initial time. So there is a signal that was intentionally introduced by humans and random noise. Okay, so if you want to see good old times when we didn't have this influence, you may want to set up the values of percent and amplitude to 0, and then it will be isolated two-level system evolution. So if you want to double check that everything, there is some limit when we can trust this approach, we can set up an approximation that we neglect influence of this random environment. So I'm changing this percent and AMP0 to 0 and rerunning. So you see the picture became much more cleaner. So you have ground, excited, some off-diagonal elements, and then they do not change with time. Right? So this low amplitude random field contributes to change of the population. But right now, in the experiment that we did without this these non-zero values for these parameters, the dynamics of the occupations was looking random. We cannot say that it is slow relaxation in some specific trend. It looks also rather random. But here is the hypothesis. If we repeat the same procedure for several modes, then in some aspect they will interfere constructively, in some destructively, and in average, the red line will start going slowly, continuously, with much less noise downwards, and the blue line will start going with much less noise continuously upwards. Make sense? Okay, let's try to do this experiment by running this code with longer name. And let's see what it does. So it has the same unit for the random field. And in addition, we do have cycle over different representatives of ensemble. So in the original code, we had only one loop over time steps. And when we started doing dephasing and photon echo, we added another loop on the top of it, averaging over representatives of ensemble. Here, there is the same one. So by going from one to another representative of ensemble, we are doing nothing. We assume that it is the same frequency, but the random field will be recomputed again and again with different random numbers, which you model that each of the representative of ensemble will be coupled to a different mode. Same frequency, but different randomness. So if your computers are not performing video recording, on your computers it will be like 40 times quicker. So it should give the numbers 1, 2, 3, 4 for each representative of an ensemble. And when I'm not doing the recording, it goes like in 30 seconds. But now it is delayed a little bit. So while it is going forward, I will probably make a tour around the seats and see what is going on at your sites.
No. How many ensembles? Like 30?
40.
40. So
Infinity or infinity equals 40.
40. She has 36 more to go.
So what?
It's the black one. Yeah.
So
Right?
what
Black
are your
is average, right?
Mhm.
So like,
Well, okay, I need to.
oh, I think I just lost my. I gotta return.
So what is the thick red and thick blue lights?
I would assume that
More stuff overlapping.
Huh?
Stuff overlapping?
Those are occupations,
average.
average occupations. After you perform average over ensemble. So what are your observations about the blue and red lines? How do they behave in average?
About the same as without the background field.
Okay. But do they stay constant, or do they fluctuate, or they change?
They slightly go down, or they slightly.
They approach each other. So you may try. Well, my small computer will not be able to match it, but you may try to increase the value of amplitude A and P0 at the very beginning of the script. Make it 2 times bigger. This is so much quicker.
I must have a better processor. Hopefully that. And I have solid state. They do? Oh, that's why this says SS. So these are solid state? And why is it SS? Oh, I'm done. Oh, okay, that's terrible. Whoops.
No, it's very artistic, but you may recognize that there is a thin lines and the background.
Here.
And we can actually redo the image so that it doesn't show this individual lines over an ensemble.
Yeah, so you can see that they go to about 50-50.
They go to 50-50 and they go much quicker. Right?
Oh, what was your number? No, what was your number? Oh.
So you have
That
blue
just-
and red approaching each other.
Oh, I know.
200?
15 milli, whatever. So it was this. And I just deleted it.
Oh, mine is on the halfway. So how do we interpret it? Just let's try to develop a verbal formula. What are conclusions? If we would be experimentalists who look on the instrument and try to write a paper.
The presence of the fluctuations, their population
Facilitates
side of state
uh-huh,
and the ground state.
facilitates the relaxation of both excited and ground state to some thermal equilibrium value.
Oh yeah.
Okay, and the higher the amplitude of this random fluctuation, the quicker occupations of ground and excited approach this thermal equilibrium value. Right? Good. You are done. This idea? What?
Yeah, I did
They're
that.
cheating. They're not supposed to keep a 0.05.
Okay, you know what I
They're
think?
making this so big.
Yeah.
Do you have an idea? Do you have an idea why it comes to 50-50? just used your background and scientific intuition.
Your phases, dephasing, some might be fully populated in the excited state, some might be fully populated in the ground state. When your average cells is your dephasing times different.
Okay. Consider Fermi distribution.
The energy present is much greater than the difference between.
Yes. Yes. What do you know about Fermi distribution?
Are we at finite temperature?
Yes.
That's 1 over like e to
Equations are boring. I'm sorry to say, being an instructor, but let's think qualitatively.
At infinite temperature, Boltzmann distribution gave us a two-level system with half of population.
Yes, good. And if we apply Fermi distribution to two-level system at 0 temperature, lower state will be 100% occupied, higher state will be 0% occupied. It is what you always see in what we use as an input data for Slater determinants for ground state in computational chemistry, right? Use only occupied orbitals. But if we raise the temperature and use the equation that we were trying to reproduce, but we don't need now, the occupation between ground and excited will smear out. The higher the temperature, the larger fraction of the population moves from ground to excited. But it will never be inverse if we are in a thermal equilibrium. So as soon as we approach very, very high temperature, they will approach the distribution 50-50. And then the transition, intensity of transition from excited to ground and intensity of transition from ground to excited will be the same, will be equally probable, which is in fact modeled by this semi-classical bath, what Levi was trying to say. I don't remember, but it sounded very right to me.
I was just saying, if you look at the balls,
We can cut what we do not like in the recording. You want to say spherical diagrams?
yeah, so if you look at your phase, even though we don't really know the phase, if the phases are random, then at a certain time, then they should have equal population.
Mm-hmm. Yes. And you provided the mechanistic explanation. And Jabet suggested the quantum explanation based on the... yes. Yes, I am.
Oh, is it hot? Although.
No, it is not the right one. It should... no, it should look... maybe it's still...
Maybe you have two figures open.
Oh, no. It was taken...
Oh my god.
It was taken a little delay. So, what are we looking at? If we look on this thick blue line, it shows the overall occupation of the excited state upon photoexcitation. And you see, as time goes by, it gradually decreases. And same happens with the thick red line, where the occupation of the excited state, ground state, raises. And these thin lines correspond to individual representatives of an ensemble. Some of them go quicker, some of them slower, and they look randomly. But in average, it is relatively smooth decay. If you take more representatives of the ensemble average, it will be very close to exponential decay. In case you are practicing surface hopping modeling, you are getting the same figures, but they cost million times more expensive. You are computing non-adiabatic couplings, atomistic trajectories, but then you also do average over ensemble to get this noisy figures of relaxation, right? But here we show that this noisy type of relaxation is a general trend that you can obtain for much cheaper numerical effort, especially if you are not doing video recording. Right now, we do not have explicit homework based on this code. Just enjoy it. We may plan on some homework later, but what you did today by observing, running this code, and trying to run it at different parameters serves as the very important step in description of relaxation phenomena. So we didn't cover the whole area. We covered only semi-classical approach where the bath environment is randomly fluctuating classical ensemble. But we see that in principle it does give a relaxation. When we meet tomorrow in class, we will try to get the same results by pen and paper derivation. In fact, in class we have introduced two decay constants: transversal for decay and longitudinal for relaxation, right? But so in principle, we know what we are going to obtain in any experiment or through modeling. But right now, our purpose is to get atomistic background, atomistic protocol to compute these relaxation constants, to determine how to find them, whether they are connected to Fermi's golden rule, and if Fermi golden rule, what is this coupling, what is the density of state, or maybe it is something more complicated. I think we are done. Feel free to ask questions, but formal part of the meeting is complete, and I look forward to see you tomorrow at noon in class.
No idea what you I can turn my own laptop. No one.
That's a good idea. Yeah, really famous.
It is in our inbox.
Really good now. Yeah,
So, off flight Sunday, right?
Okay, good night.
Off flight Sunday? Our flight is Sunday. Do you know what time?
What day is your flight?
We have to start early morning.
Sunday from Minneapolis. Well,
I think ours is the 16th is Sunday, right?
yes.
Are you flying on the same flight?
No, I don't know.
I don't remember which company you're flying with.
Delta.
Maybe.
But
But Delta has several flights.
they're flying a day earlier than us back.
Yes.
And they got first class tickets, so.
No. This time we are flying for like 180 round trip.
Oh wow, that's cheap. Ours is like 2 something?
15, something like that.
Yeah.
Other things are the cheapest one.
They
Oh, yeah.
they're